Okay, so now we're going to discuss the probability of two independent events. And so mutually exclusive, or in other words, disjoint events, is different than independent events. And so we just want to make sure that we understand these differences. So suppose two events occur, A and B, and if the probability of event B occurring is the same whether or not A occurs, then A and B are independent. So for example, if I have the second event occurring, is that second event affected by the first event? That's different than mutually exclusive, right? Because disjoint event says there's no overlapping outcomes, right? But independent events saying that the second or the following probability is not affected by the first. Let me give you an example. If I wanted to roll that six-sided die and I rolled a 4 first, and on the second toss, will that toss and what it lands on be affected by me rolling a 4 first? You're like, well, no. You're like, oh, well, you would blow on it for good luck, right? And all this stuff. No, but just think of it logically, right? Yes or no. I roll a 4, I toss the dice, I roll a 4. I'm going to toss it again. Does me tossing a 4 first affect how this one's going to land? Probably not, right? So tossing a die twice or more than once, those are independent events because the following events are not going to be affected by the previous one. However, what about a deck of cards and you're playing, let's say, poker or something, and you're dealing cards? If I have a deck of 52 and I draw a card, and I'm not going to put it back because we're playing Go Fish or something, right? And so I pull out a card and then I pull out another card. How many cards left in that deck on that second draw? There's not 52 in that deck at all times, is there? There's 51 on the second draw. And then there's 50, 49. And if you're dealing 5 cards to this person first, that's 47, or let's say 1 card round, that is 47 cards left in the deck. So by the time this next round of 5 cards go out, you only have 47 cards left in this deck. And the next draw will be affected because there's less cards in the deck and other cards are already dealt out. So you have to think about the following probability and is that going to be affected by the first. Disjoint events, which we just discussed, means that outcomes happening at the same time. So it's a little different. Let's talk about when Satchel draws a card and he puts it back in the deck before drawing another card. What if Satchel draws a card, which is a spade, and does not replace the card back? Now let's say Satchel draws a heart. If Satchel had replaced the spade before drawing the heart, how would this probability be different when he did not replace the card? So there's two situations happening here. There's one where he replaces the card, and another place where he doesn't replace the card. Okay, so let's look at, he draws the card to be replaced first. Let's look at with replacement because that's what we've been doing. And so here's the first card and the second card. And these are the probabilities. So the probability of drawing the spade on that first deck was 13 out of 52, right? Because we know there's 13 spades out of 52. He puts that card spade back and now pulls for another one, which would be a heart. Well, how many hearts there? 13. And how many cards left? 52, because he replaced the card. Okay, now let's look at doesn't replace the card. So now if he has 2 cards he's drawing on the first and second, and these are the probabilities. Okay, so on the first draw is going to be the same, right? Because there's 52 cards in the deck and there's 13 spades in there. So no matter what, this first one will be not affected by anything because it's just the first probability. But now Satchel holds the card in his hand. So there's one less spade, one less card. So when he goes in for the heart, how many hearts are in there? Well, the spade's not a heart, right? So there's 13 hearts in there. But how many cards left in the deck? There's not 52 because he's holding on one, and there's 51 left, right? So let me write a little note. So again, this one is the spade, and this one's the heart. The first draw is always the spade, and the second's the heart. And then we notice that this is going to be a little different, right? And so we can see here that if he draws the spade on the first try and replaces that card back, there's still 52 in the deck. And that total number of outcomes stays the same. But if he doesn't replace the card, right? And so now he draws a spade, but he's holding the spade. He does not put it back. And there's one less card in the deck. Does the second probability change? Yes. So here, these are not independent events. And these are independent events. So anytime there's a replacement or on the second or following probability that you're about to do, that there's the same number of outcomes for each draw. Every single one is every single probability or chance is likely to occur, right? Every event. And doesn't replace the card means it's not independent and that following probability will change because not every event is likely to happen, especially as you're pulling out the cards. But let's think of this in a little bit more applicable sense. Let's talk about raining, right? When we said, suppose it will rain in Houston, Texas, and also rain tomorrow in Galveston, Texas, a city near Houston. Okay, are these two independent events? So this example is sometimes challenging for students because they're like, yeah, they're different cities, done, right? Like Texas, Galveston can't be Houston, and Houston can't. But that's disjoint events. You're right. Cities are disjoint because if you're in Houston, you're not in Galveston, and Galveston, you're not in Houston, and there's no overlapping outcomes. But we're not talking about overlapping outcomes. We're talking about disjoint outcome. We're talking about independent outcomes. And is the second outcome affected by the first? If it rains in our city next to us, what are the chances it's going to rain in our city? So let's think about it. I am in my next city over, right? And that could be as close as your Costco next door. If it rains there, are you most likely to get some rain on your way home or on the next city over? Well, yeah, we are. There's a storm out in Florida, hurricane. Are we going to see some of that effect, over here if it goes through the South and the Gulf and all that? Yeah, probably. So weather is very dependent on what's happening in other parts of the world. And so are these two independent events? And we would have to say no, because if it rains in a nearby city, most likely it will rain in the next city. And so we just want to make sure that we understand these differences when we think about dependency and independent events versus disjoint events. Okay, so the problem, what's the formula, Darlene? So the probability of two independent events. So two independent events, which means that essentially you're replacing it and each outcome is likely to happen, right? Is the product of the probability. So we denote multiplication with independence. So what is the probability of Satchel drawing a heart, replacing the card, then a spade? So the fact that he is replacing the card tells me that I'm going to have the same number of cards on each draw, and these will be independent events. And so the probability of Satchel drawing a heart and a spade is equal to the probability of drawing a heart first times the probability of drawing a spade next. So the probability of drawing a heart we already know is 1/4 from a previous example, and the spade is 1/4, so it'll be 1/16. So the fact that these are independent events, why? Because one event doesn't affect the second. Okay, so let's just keep the momentum going. So if we keep going, let's look at this table. It's called a two-way table, and we're going to do more with that in a little bit. But we just gives you an idea of a table where we have the hand that people write with by gender. So we have a total of 100, right? 50 female, 50 male, but the fact that they're right or left-handed is different, right? It's not even. There are more right-handed people than left-handed people in our sample. So let's just say the probability of finding a randomly selected individual to be male and left-handed. So let's find the probability of male and left-handed, which is the number of people that are going to be male and left-handed over the total number of outcomes. Well, in our case, we're talking about people, so we'll say total people. Okay, so to be male and left-handed, so male and left-handed, those gives us some overlap, right? So that would be 12 over 100 people in my sample. Okay, and then we could reduce this or see that it's 0.12 or 12% or 3/25. Okay, so now let's go ahead and find the probability of a randomly selected individual to be male or female. So the probability that you're male or female would be equal to, and again, male or female, that's your red flag, and you're like, ooh, this is going to be add, and are these going to be disjoint? Are there any overlapping outcomes? Meaning, can the male be female and the female be males? Well, in this sample, they're not. They're designated, right, by their gender. So there is no overlap with, again, columns, right, male and female. See, there's no crossover. The moment I do a crossover of, let's say, males left-handed, I see that there's an overlap. So anytime there is a crossover with horizontal versus vertical, then we're going to see that it's not disjoint. So we'll say disjoint because no overlapping. Okay, so this would be the probability of being male plus the probability of being female. Well, you're like, well, the probability male or female, all I have are male and females. Like, that's certain that no matter who I select, it's going to be male or female. I would agree. And I would say, yeah, it's certain, meaning this probability is probably going to be 1. And so let's see. So there are 50 out of 100 people to be male plus 50 out of 100 people to be female, which is 100 out of 100, which is 1. Or 100%. And you're absolutely right. This means we're certain. No matter who we select, we're going to have a male or female. Okay, this next one's going to be a little tricky, and so we just want to be careful when we read this. So the probability of randomly selecting an individual to be a woman, given she is right-handed, given that she is right. So are we looking at everyone, or they're telling us who to look at first and then take somebody and grab from them? So the probability that it's a woman given to be right-handed. What this is saying is that find a randomly selected individual that's a woman, given that she's right-handed. So are we looking at males at all? Or maybe if they're right-handed? Or are we looking at left-handed people? Well, not if it's given that she's right-handed. So it might be a little challenging, but let's think about this. I tell you, go look at right-handed people. Now take your hand and grab a name out of a hat. What is the probability that that person's a woman? So what I'm doing now is I'm limiting who I'm looking at. I'm only looking at right-handed people. And now I want to select somebody in here of the probability of woman. And then here are males, right? So I'm only looking at right-handed people. So if I wrote this, sorry. So the probability of a woman given to be right-handed, right? So this line here means given in math. There we go. And that would be equal to the number of women and right-handed over the total right-handed people. And that really comes from, given she's right-handed, you're only looking at right-handed people. So what is it? So the number of women and right-handed, that's 42. And the total of number of right-handed people was 80. So in that case, that would be 42 out of 80, which is 21 out of 40. Okay, and then if I put this in my calculator, it would come out nice, like 0.525 or 52.5%. Okay, so just to recap, recall that independent events are events in which every outcome is likely to occur and following events are not affected by the first event. And here, notice that if we had a given that she's right-handed, we had to change our denominator. Whereas the previous two examples, we had the denominator to stay 100, the number of people in our sample. But the moment you start isolating the groups of people and grabbing from there, that's almost like the type of sampling that we've discussed in the previous chapters. So independent events are just events that the following events are not affected by the first, and disjoint events are the events in which there are not overlapping outcomes. The last piece is we're just going to talk about the probability of at least one. And the probability of at least one is just 1 minus the probability of none. And if I just take a simple example like I have here, and I say, well, what is the probability of at least 5 occurring when the sample space are the positive integers from 1 to 100? Well, of at least 5 occurring would be the probability of 5 or 6 or 7 or 8. And am I going to add 95 probabilities together? Or can I work smarter, not harder, and say, well, this is actually going to be 100% 1 minus all the probabilities less than 5, right? So for plus the probability of 3 plus the probability of 2 plus the probability of 1 plus the probability of 0. So essentially what you're doing is you're taking the 100 and you only want 5 to 100. And so you're just going to take everything here, which is only, 5 probabilities versus 95. So the probability of at least one just makes it a little bit simpler. And so we just have this formula that says, okay, well, the probability of at least one is equal to 1 minus the probability of none. So according to Master Foods, the company that manufactures M&Ms, they say 12% are peanuts, peanut M&Ms are brown, 12 are yellow, 12% are red, 23% are blue, 23% are orange, and 15% are green. If you randomly select 3 peanut M&Ms, compute the probability that at least one of them is green. So there's a little bit happening here. So let's go ahead and jot this down. So the first thing is that we are selecting 3 M&Ms. Okay, and then we want to see that of these 3, at least one is green. Okay, well, how many are green? 15% are green. So how many are not green? Well, I guess you could add up all the percentages that are not green, or just know that it's 100% minus 15, which would mean that 85% are not green. Okay, so going to the problem, the probability of at least one is green, right, of the 3, is equal to 1 minus the probability that none are green. And what this means is the probability that the first M&M I select is not green, and the second one I select is also not green, and the third one is also not green. So let's just go ahead and take a look at this really quickly. So once again, I'm selecting 3 M&Ms, right? And I want to see if I go in there in the pot and select one of the 3, what's the probability that they are green? And that's just 1 minus the probability that they're not green. And so if 1 minus the probability that none are green means that when I select 1, 2, and 3 of them, that all of them will turn out to not be green. And so it'll be 1 minus, well, what is the percentage of the first one not being green? Well, that's what we looked at over here. And we said, well, 85%. We're like, yeah, so 0.85, and which is multiplication, right? The second one is also not green, which we said was 0.85, and 0.85. So essentially, this is just going to be 1 minus 0.85 cubed, and then we can always go to our calculator to calculate that. So if I go to the calculator, I'll have 1 minus 0.85 cubed. And so I get 0.385875. Okay, and then which is also going to be 38%, 0.5875, or, and then if we wanted to change this answer to a fraction, we could just go to math, go to frac, enter, and it'll give me the fraction that's equivalent, which is 3,087 over 8,000. So any of these should work. But what does this really mean? If I really wanted to interpret this probability, this would mean that there is about a 39% chance at least one of the one of the three randomly selected M&Ms is green.